Today we want to talk about parameterized curves. We want to describe a one-dimensional curve in R3. That's our goal. So we're going to start by describing one-dimensional curves in R2 by parameterizing something. So we're going to go back and we're going to parameterize a curve in R2. It's not really, it's going to be an example. Actually, before we do this, let's just write down the big idea of parameterizing a curve. Instead of defining some kind of relationship between x, y, and z, we're going to define x, y, and z independent of each other as functions of some parameter. So the idea of parameterized curves, instead of defining x, y, and z, instead of defining x, y, and z by their relationship to each other, for example, in a function or an equation, we're going to define them independently as functions of some parameter. Usually we'll use the parameter t. Because calculus is essentially an engineering class, we're looking at change. We're going to be looking at change over time, so that's our default. So the curve is the collection of points x of t, y of t, z of t. We usually have to specify some range of values of t we're going to plug in. So t for all real numbers, or t between 0 and 2 pi. Those are going to be two popular choices. Sometimes we go with t between 0 and 1, because that's convenient for us. So to plot the curve, instead of picking values of x, y, and z, we pick values of t and see what point they correspond to. So if we plot the curve, by plugging in values of t. For example, I'm going to do one in R2. For example, I've defined x as a function of t, I've defined y as a function of t, and I say apply this to all values of t. If we want to figure out what this looks like, we're just going to plug in a bunch of values of t and figure out what x is and figure out what y is. So for example, if t is equal to 0, x is equal to 1, and y is equal to 2. I choose a value of the parameter. I figure out x independently of y. Then I go figure out y independently of x. X and y aren't related. We'll see that they are related, but they aren't related as far as the parameterization is concerned. It should. We see this a lot. First shows up in true. If t is equal to 1, then I get x is 1 plus 3 or 4, and y is 2 minus 1 or 1. If t is 2, x is 1 plus 2 threes or 7, and y is 2 minus 2, which is 0. We can plug in negative values as well. Then our table will look a little bit messed up. So oh well. If t is -1, then x is 1 minus a 3, -2, and y is 2 minus 1 or 3. We're choosing values of t and figuring out x and y independently of each other. That's how this table operates. We're choosing values of t and we're finding x and y independent of each other. We're not choosing x and finding y or choosing y and finding x. X and y are determined by t. Unsurprisingly, we are creating a line when we do this. So I've got the point. So when t is 0, we're at the point 1, 2. When t is 1, we're at the point 4, 1. When t is 2, we're at the point 7, 0. When t is -1, we're at the point -2, 3. And when t is -2, we're at the point -5, 4. We can see we are creating a line. We are not surprised that we are creating a line. X is linear, Y is linear. We're going to make a line. If everything's linear, we're just going to get a line. This is different than the lines we've had in the past. By parameterizing this line, we have given something that this line something that lines have not always had. Notice that each of these points corresponds to a different value of t. The 0 for t is the point 1, 2. So at this point here, this is where t is equal to 0. This is the point where t is equal to 1. Here's the point where t is equal to 2. Here's the point where t is equal to -1. So one thing to note is that not only are we creating a one-dimensional curve in R2 by parameterizing it, we're not just creating a line. This line has an orientation. This line has a direction. So note that by parameterizing the curve, we assign an orientation to the curve. So this is not just a line sitting there in R2, this is a line with direction. As t increases, the line goes that way. So I can indicate that direction with this arrow. So it's not just a line anymore, it's been parameterized, so it has direction. The line can be described with a vector. The line itself is not a vector, but it can be described with a vector, which is a great question. What vector describes this line? So notice that as we go from t equals 0 to t equals 1, x increased by 3. As t goes from 0 to 1, x has increased by 3. No surprises there. As at t goes from 0 to 1, y has decreased by 1. No surprises there. If we look at x prime and y prime, we get the components of the vector that describes the direction of the line. So x prime of t is 3, and y prime of t is -1. We see that showing up in the table. Plus 1 plus 3 is 4, plus 3 is 7, 2 minus 1 is 1, minus 1 is 0. This is a vector 3, -1 that describes the direction of the line. Because from t equals 0, if we go 3i minus 1j, we'll go from 1, 2 to 4, 1. Is this compatible with stuff that we already know? Math always has to be backwards compatible. If we get a new thing and it doesn't fit with the old stuff, then we need to fix the old stuff or fix the new stuff. Something is broken. So this is a line, and in our experience, we've always described a line with slope. Slope is change in y divided by change in x, delta y over delta x. Derivative is change. So slope is change in y divided by change in x. This is a line, so these changes are always the same. Y is decreasing by 1 when x is increasing by 3. Y is decreasing by 1 when x is increasing by 3. Just like we saw in the vector describing the line. This is a line with a slope of -1/3. So it's not that x and y aren't related. We can write a relationship for this line, but that's why I picked a line so we can easily relate the relatively new thing, parameterizing a curve, with a very old thing, equation of a line. Any questions? Comments? I changed the sign of the coefficients of t. I kept the 1 and the 2, but I changed the 3 to a -3, and I changed the -1 to a 1. What will this do to the curve? If we plug in points, plug in values of t, we start getting a familiar collection of points. When t is equal to 0, we still get 1, 2. When t is equal to 1, we get 1 minus 3, -2, and 2 plus 1, 3. When t is equal to 2, then y is 4. And x decreases by another 3, so -5. If I start going the other direction, at -1, 1 plus 3 is 4. And at -2, 1 plus 2 threes is 7. We start to get a familiar collection of points, but we're going the other direction. Same line with the opposite orientation. We get those same points, but we're going in with the opposite orientation. If I look at the derivatives, x prime of t is -3, and y prime of t is +1. So our vector describing the direction, a tangent vector to this curve, is -3, 1. That's just the opposite of what we had before. Just -1, times 3, -1. It's the opposite orientation. If we look at the equation of this line, our delta y is 1 this time, but our delta x is now -3. So our slope is still -1/3. So our equation will still be can still be y equals 2 minus 1/3 times x minus 1. When we write the equation of the line with x and y, when we describe it as a relationship between x and y, we don't have the orientation going along with it. It's not always a good idea to simplify things. Questions? Is everybody okay? Everybody looks so stoked. We all look like this.
I mean, just two more.
You're not thinking about parameterized curves right now. You're thinking about spring brain. It doesn't matter what I say right now. It's just like, I just need to give spring brain. Just shut up, Leach. Actually, don't even bother shutting up. Just don't ask us to do anything. If I see the cards come out, I'm walking out. I noticed that you haven't pulled out the markers or the boards of the classroom, so we feel pretty safe because there's only 15 minutes left. And it takes 15 minutes just to get that shit set up, so all I have to do is wait.
I mean,
2 more days.
spring, I mean, we want spring break, so we can do that.
Correct, that's the correct answer. I ain't paying you during spring break, so I mean, I wouldn't do nothing either. That's one of the perils of having a job in academia. Everybody knows when you're not working. So they're like, plan. So I go, oh, maybe we should move. When should we move? I go, how about the last week of March? Why is that? Leach will be on spring break. And we can get some free labor. Let's take care of that over the summer. Why is that? Because Leach will be on summer break.
I mean, isn't that the same for students?
Well, my big mistake was I told people that I don't work in the summer anymore. It's like, oh, I'm taking summers off from now. Oh, really? I'm going to be moving. Oh, dang, look at the time. I'm going to have to go back to work during the summer. Any questions? So, well, the big idea here is not, so first of all, we want to recognize that we can describe all the stuff that we were able to describe before. We don't miss out on describing functions. We don't miss out on describing equations. We've got a new way of describing things. One of the things that this parameterization brings to the table is a direction. We have, so now our path through R3 is going to have some kind of direction along with it. We're going from point A to point B. It's not just some curve in space. It's a path from one point to another point. Actually, we're going to be using point P and point Q. From point P to point Q, traveling through space. That's what we want to think about. Notice that I implied something. I just like straight up just took some derivatives with respect to t and say, hey, look at that's a vector. What vector is that going to be relative to the path? It's hard to see on this particular curve, but if I've got some curve running through space and I take the derivative of each of the equations in parameterized form, what is that going to be? I don't, this is a surface, this is a curve. What is that vector going to be? Not quite the normal. What's it telling us? It's telling us the direction that we're going. That's what the derivative says. The derivative says we're going that way. So what is that vector going to be relative to the curve? I'll put my curve back. There's a vector.
It's going to go down.
It's going to be tangent to the curve. So it makes sense that it's a tangent because how do we find it? We took some derivatives. That's what the derivative tells us. The derivative tells us what direction we're going. In this context, we're going to be making a vector to describe the direction because we are in R3 now, and I need a vector to describe direction. This was in R2. And we kind of cheat by describing the direction with negative 1/3. But that assumes that we're reading from left to right. Now, it don't matter. -3, 1. That's the direction we're going. We're going -3, 1. I pointed the wrong way. I was actually just upside down. Earlier, I was doing some research in the southern hemisphere and everything was backwards. So.
Hey, oh yeah, the y equation messes up with the
So our derivative is telling us our tangent. Speaking of upside down, last thing today. Damn it. This n is upside down. Does everybody see that this n is upside down?
Yeah.
Who sees that this n is upside down?
Okay, yeah. Okay.
If you don't see that the n is upside down, that's okay. You're probably better off. But it bothers me every day that I'm in this room. 5, 6, 7, 8, 9 hours a week I'm in this room. And I have to look over here at this upside down n.
Is it upside down?
No, it is upside. It still goes up, down, and up again. And it's just. And it's laminated, so I can't get it out of there and fix it. And I can't go tell them about it anymore because the restraining order prevents me from going to this part of the building. I'm just kidding. I don't have a restraining order. It expired, so that's where I'm going right now. All right, that's going to do it for today. So remember the big picture stuff. Vector fields, vectors everywhere. Path through the vector field. That's it for today. I will see you all on tomorrow. Everybody have a good day, and thanks for playing.
Hi, Professor. Have a nice day.